Hello, welcome back. This is 4-4 related rates, and this is the third video. In this example, we're going to go ahead and look at 3 examples that show related rates and how we can solve them. So here we go. All right, continuing in the notes, example number 8. We have a balloon is rising vertically from the ground at a rate of 3 feet per second. A person standing 75 feet away from the point on the ground directly below the balloon. Okay, they say, part A, find the rate in feet per second that the distance between the person and the balloon is changing when the balloon is 40 feet above the ground. All right, so these problems, easy as pie. P stands for picture. Do you have a picture? And yes, I do have a picture, which is already given to us here. We are missing something. I am missing, they talk about a person. So here's a person standing 75 feet away from the point directly below the balloon. And we want to find the rate between how the distance between the person and the balloon is changing. So I'm going to label that with a variable, and I'm just going to label it Z, since they already have that other side as Y. So there's my picture. Okay, what information do they give us? What info are we given? PI, so PI, the information. Now they tell us that the balloon is rising vertically. This balloon is going up. So the rate that Y is changing is equal to 3 feet per second. So there's dy dt. Okay, I know that the distance between the person and the point below the balloon is 75 feet. They say find the rate that the distance between the person and the balloon is changing. Okay, so we need to find dz dt. This is what we need to find when, I'm going to erase my equal sign here. I'm going to put when they say the balloon is 40 feet above the ground. Okay, so that's when y is equal to 40 feet. Okay, so there's my picture, there's my information, PIE, easy as pie, and we now need an equation. So what equation ties all of this together? The Pythagorean theorem. So I have 75 squared plus y squared is equal to z squared. Now I want to go ahead and talk about this setup. I'm plugging in 75 here because that distance is constant. And going back to our picture here, this distance is never going to change. So if you have a constant value in your equation, you can go ahead and replace it. That makes our differentiation so much easier because the derivative of a constant is 0. So you'll want to plug those in. Now y, this balloon's rising, so y is changing, and then the distance between the person and the balloon's changing, so I must leave those as variables. Okay, so there's my equation. I'm going to go ahead and I'm going to differentiate now. So the derivative of 75 is 0. The derivative of y squared is 2y times the derivative of y with respect to time. And same on the right side. So the derivative with respect to time of z squared is 2z dz dt. Okay, now we're just going to go ahead and plug in the information that we have. I know that dy dt is 3. Okay, so I have 2 times 3 feet, or sorry, that's y. 3 feet per second. And then they want to know how is the distance between the balloon and the person changing when y is equal to 40 feet. So I know that y is equal to 40 feet, okay, is equal to 2 times z. Now z I do not have. I'm going to have to go ahead and find it. And then dz dt, this is what we're solving for. Here's what I'm solving for. So I've reached a point where, hey, I need to go ahead, I need to go back, I need to solve for z. Okay, how do we do this? Well, going back to our image up here, I know that the distance of this side length is 75. At this moment in time, I'm calculating when y is equal to 40 feet. So if I have 2 side lengths, I can go ahead, I can find z. I have 40 squared plus 75 squared is equal to z squared. So therefore, z is going to be equal to the square root of this quantity, and that gives us 85 according to my previous calculations, 85 feet. Okay, so I'm going to go ahead, plug in 85 feet, and then now I just need to go ahead and solve. So dz dt is equal to, on the left side it looks like we have 6 times 40, which gives us 240 feet squared per second, divided by 2 times 85, that's 170 feet. Okay, and if we go ahead and we could have just reduced by 2, that's 120 over 85 feet per second. So that's how fast the distance between the person and the balloon is changing. All right. Part B. Part B, at what rate is the angle theta changing in radians per second when the balloon is 40 feet above the ground? So again, my picture and my information is not going to change. What's changing is my equation. So going back to my image here, I want an equation that ties in theta and ties in the side y equaling 40. And now I know that this side is 75. Okay, well, using good old SOHCAHTOA, sine of an angle is the side opposite over the side hypotenuse. Cosine of an angle, theta, is equal to the ratio of the side adjacent divided by the side that's hypotenuse. And tangent of theta is the side opposite divided by the side adjacent. So SOHCAHTOA, there we have it. And it looks like I have information about the side opposite. And I have here the adjacent side. So I'm going to use tangent of theta. So that's going to be my equation here for part B. I have tangent of theta is equal to, and that was y over 75. Now again, I'm going to leave y as a variable, not as 40, because that value is changing. Now I'm going to go ahead, I'm going to differentiate with respect to time. So the derivative of tangent is secant squared theta, now times the derivative of theta with respect to time, so d theta dt, which is equal to, the derivative of y over 75 is just 1 over 75, times the derivative of y with respect to t. Okay, so there's my equation. And I want to solve for d theta dt. So I need to go ahead and plug some information in. I'm missing, first of all, I am missing nothing on the right side. I have 1 over 75, my dy dt, that's the rate that the balloon is rising, and according to the last problem, that is 3 feet per second. Okay, and on the left side, I have secant theta. I'm missing that. That's secant theta quantity squared. So I need to find secant theta. I gotta find it. Now, a lot of you may freak out about that, but just calm down. Secant theta, isn't secant theta the reciprocal of cosine, right? This is an identity that we learned. Secant theta is 1 over cosine, and you can write it like this, or I can say, okay, what's cosine theta? I'm going to find cosine theta, and then secant theta is just going to be the reciprocal of that. So I'm going to go back to my triangle, which is here. Here is theta, okay, and I want cosine. So cosine theta is the side adjacent over the side that is hypotenuse. That is the hypotenuse. So adjacent, 75. The side hypotenuse, 85. And that is, again, because this is at the moment when y is equal to 40. So y is equal to 40. I already determined that that side was 85. Okay, so adjacent over hypotenuse, 75 over 85. So 75 over 85, which means that secant is 85 over 75. All right. Okay. So, and I can go ahead, I can reduce that. So by 5, that's going to be 17 over 15. Okay, so I found secant theta using my given information, right triangle trigonometry. So we have 17 over 15, quantity squared, d theta dt, and this is equal to 3 over 75. Okay, and I'm going to go ahead and I'm going to just solve. So d theta dt is equal to, well, I'm going to cancel this out. I'm going to multiply by the reciprocal. So 15 squared over 17 squared on both sides. 15 squared over 17 squared. And we end up with, if I reduce this by 3, 1 over 25, we end up with 15 squared, which is 225 times 25 times 17 squared. And I'm just going to leave it like this. And again, this is in radians per, and I think it's second. Yeah, radians per second. And they tell us this in the problem. In radians per second, what is it? So there you go. There is your numerical value. You could plug that into a calculator and find an approximate answer, but that would be suffice for a free response question. Okay, example number 9. Example number 9. This one's fun. We have two planes that are traveling towards an airport, okay, and they're given here, A and B. And it says plane A is traveling due south at a rate of 200 miles per hour. Okay, so here's plane A. This is my picture, and it's traveling due south, so it's going that direction. And let me get this. Plane A due south at a rate of 200 miles per hour. Plane B is traveling due west at a rate of 250 miles per hour. So here's going due west. Okay, they're both flying towards this airport. And then it says, let x and y represent the distances between the planes and the airport at time t. All right, part A. Find the rate that the distance between plane A and B is changing when x is 400 and y is 300. Include units of measure. Okay. So I'm going to go ahead, I have my picture, I already kind of know what's going on. The only thing maybe missing is this side, the distance between the planes. We haven't labeled that, I'll call that Z, that's going to change. And now I want to go ahead and label my information. So what is given in the problem? So they tell us how plane A is traveling due south at 200 miles. Well, that's a negative 200 miles per hour because that distance is decreasing. So that is dy dt. That's how y is changing. Negative 200. Okay, then they talk about plane B. They say that plane B is flying towards the airport at a rate of 250 miles per hour. And again, that distance is negative. That rate of x is negative because it's flying towards the airport. And then here they want us to find how is the distance between the planes changing. What is dz dt at the moment that x is 400 and y is 300 miles. We don't know this. We got to find this. Okay, so there's my information. All right, what's our equation? What is the equation to tie sides of a right triangle together? Good old Pythagoras. We have x squared plus y squared is equal to z squared. All right, let's differentiate with respect to t. So we have 2x dx dt plus 2y dy dt, and this is equal to 2z dz dt. Okay? Now, according to our problem, we're already given a lot of this. I know that x is 400 miles per hour. 400 miles. I know that that plane has a rate, dx dt is negative 250 miles per hour, plus 2 times y is 300 miles, times its rate, which is negative 200 miles per hour. Okay, this is equal to 2 times z. Something I do not know. I do not know what z is. I'll find that in a moment. And again, dz dt, that's what we're after. So I'm going to go ahead. I need to go back to my initial equation. And at the moment, I'll use an arrow over here, that x is 400. This is 400 squared plus 300 squared is equal to z squared. You can go ahead and calculate that, or something you can do is you can recognize that as a Pythagorean triple. I have multiples of 100, and this triangle is a 3, 4, 5 triangle. So if you solve this, you will get z is equal to 500. It's a 3, 4, 5 triangle, and they're multiplied by 100. So I know that 2 is equal to 500 miles. Okay, something I'm going to go ahead and do just to make my life easier. I'm going to cancel 2. I'm going to divide everything by 2, reduce by 2. That will simplify some things. And we can also divide by 100 by everything. So if I reduce by 100, I'm going to cancel a couple zeros on these terms. Okay, so we end up getting negative 1,000 miles squared per hour plus, or actually minus 3 times 2 would be 600 square miles per hour. And this is equal to 5 dz dt. Okay, and I'm going to go ahead and I'm going to solve this, and that's 5 miles. That's miles, don't want to lose that. So we have negative 1,600 square miles per hour, and I'm going to divide by 5 miles. 5 miles is dz dt. Okay. So dz dt, if I go ahead and kind of clean this up, this would be negative 1,600 divided by 5 miles per hour. And there you have it. That is your answer. And let me see if I have that quantity over here. So negative 320. Yeah, negative 320. Miles per hour. All right. Whew. They're not that bad once you get the approach pretty consistent. It's not that bad. Okay. Number 10, example number 10. This is the last one I have for our lesson, and we're here dealing with a different type of shape, and this one has kind of a different approach as well. So here we go. They say gravel is falling on a conical pile at a rate of 10 cubic feet per minute. At all times, this is very important, the radius of the cone is twice the height of the cone. They gave you some information there. Here's the question. Find the rate of change of the height of the pile when the radius of the pile is 6 feet. Now they're kind. They give you the volume of the cone. They give you the equation. That's nice. Sometimes when the shape is not, I don't know, fairly basic, they'll give you the shape. Shapes that you should definitely memorize and know area and other perimeter formulas would be of a triangle, a circle, a rectangle or a square, things like that, it's expected that you would know those equations. So here we go ahead and then they say write a sentence explaining the meaning of the answer. Okay, so I have, first of all, I need to have a picture. I have a picture, okay, and gravel is being thrown onto this. And then 2, they say the radius of the cone is twice the height. So here's my radius, which is 2 times the height. 2 times the height. Okay, there it is. And this is getting bigger, right? More and more gravels is being thrown onto this. And so the height's going to increase and the overall volume of this pile is going to increase. So, okay, what did they give us in the problem? Well, they told us, have my picture, now I need information. All right, this is step 1, step 2. Okay, information. They told us the volume. I know that the volume is changing at a rate of 10 cubic feet per minute. And maybe you're like, how did you know that that was volume being added? Well, look at the units. The units can tell you a lot about a problem. We have cubic feet. So anything cubic, that's going to be volume. Also, too, they tell us the equation that we're going to use, which is given here. Next, they tell you that at all times, and this is important because this is constant, the radius of the cone is twice the height. The radius of the cone is equal to 2 times the height. They tell us that. So with that, we can go ahead and do a substitution, and I'll talk about that in a second. Next, what do they want us to find? They want us to find how the height is changing. So what is dh dt when the radius is equal to 6 feet? Okay, so I have all my information. That's what I want to find. Now, step 3, what is your equation? What are you going to use? Well, they tell us volume is 1/3 pi times the radius squared times the height. Now, sometimes the AP exam will be difficult. They'll give you a nasty looking equation where we have to differentiate and do product rule here. But here they gave us an out. I know that the radius is equal to 2 times the height. So what I'm going to do is I'm going to make a substitution. Pi times the radius is 2 times the height squared times h. And if I go ahead and clean this up, I have 1/3 pi. 2 squared is going to give us 4h squared. Okay, so now I have this equation. 4/3 pi times h cubed, which is much nicer and much cleaner because it's only in terms of one variable. Sometimes that happens, sometimes not. Okay, so there's my equation. Now that I've plugged that piece of information in, now I want to go ahead and I want to differentiate. So I'm going to differentiate this formula. So I have the derivative of volume with respect to time is equal to, if I use the power rule here, our 3's will cancel, and I have 4 pi h squared times dh dt. And again, dh dt, that's what we want to go ahead and find. So we're going to plug in everything that we know. I know that the volume is 10 cubic feet per, I think it's per minute, yes, is equal to 4 times pi times h squared. Now I don't have h. They don't tell me h, but what they do tell me is they tell us when the radius is 6 feet. Well, at all times, isn't the radius equal to 2 times the height? Okay, so if I just do a simple substitution here, 6 is equal to 2h, and therefore h, if I divide both sides by 2, is equal to 3 feet. So the height is 3 feet squared times dh dt. Okay, and I'm going to go ahead and divide. So dh dt is equal to 10 cubic feet per minute being divided by 3 squared is 9. Right, that's 9 times 4 gives us 36. 36 pi, and that's going to be feet squared. Right, feet times feet. So we end up having, if we reduce by, looks like, what, by 2, we have 5 over 18 pi feet per minute. Those feet, the feet squared cancel out with feet cubed, and I have feet per minute. Here is dH dt. This should also make sense too, right? Because height is a linear measurement, so it's going to be feet per minute. If it was area, it'd be feet squared. If it was volume, it'd be feet cubed. Okay, and there is our quantity. Again, you could go ahead and plug that in, but you don't have to. Now, they did ask, what does this mean in terms of context? Answer this in terms of context. Well, this means that the height is increasing at a rate of 5/18 pi feet per minute when the radius is 6 feet. That was the moment that we looked at. Okay, and there's what it means in meeting. All right, that is related rates. We looked at a whole bunch of examples. Remember, related rates, easy as pie. P, draw your picture. I, what's your information? E, what equation are you using? Then you're going to differentiate it. Go ahead, give me a thumbs up for this video. Related rates are difficult. Cheer yourself on every single time you finish an example. Catch you in the next video. See ya.